Good morning, everyone. We're recording, so we're ready to get started. Just a couple of comments about the upcoming midterm, which is on Monday. So I sent off an announcement. There is a Zoom session that's been set up, much like our regular class Zoom sessions, only this one's got required registration. So you can do that in advance and you'll get an email confirmation. And you just click the link in the announcement and it'll ask you to input your SFU credentials so that you can log into the Zoom session during our exam. So make sure you try to do that in advance. It doesn't have to be too far in advance. You can do it the Sunday night or with sufficient time before the 8:30 start of the exam on Monday morning. The exam will be sent out via CrowdMark by 8:28 a.m. This gives a 2-minute time period for any lag in emails, so everyone should have it by 8:30, and that's the official start time of the exam. For the Zoom session itself, make sure you have your camera on, your face and hands and writing space are visible. If that is something you can do, sometimes people are using, of course, their laptops, in which case they need to be able to see the screen. So you just sort of make do the best you can. The other thing I just want to make a mention of is, so you've probably heard this in your other classes as well, but academic dishonesty has been a problem over the last year due to moving into this online environment. I will say that I have filled out more academic dishonesty cases in the last year than I have in my entire career. So over 20 years of teaching, and I've filled out more in the last 1-year period. Often it's just a poor decision that's made in the heat of the moment. So don't let those poor decisions affect you potentially for the rest of your life. The department itself, the math department, and I know other departments are the same, they've assigned more FD grades, so failure with academic dishonesty, which appears on transcripts. They've assigned more of those in the last 1-year period than they have in the past, half a dozen years, 6 years. So there is, there is, in the heat of the moment, there is a bad decision that gets made, and these things can be detrimental for the rest of your academic careers. So just, act as you have all along throughout your academic career, and that is just act with integrity and honesty and do the best you can on these exams.
Hello, Professor.
Yes, go ahead.
Hi, I came in a couple minutes late. Can you just say again what you said regarding the camera thing?
Yeah. So cameras, make sure you're visible, camera on during the examination. And if you can, if your camera allows you to, and the space allows you to, try to have your head, your hands, and your writing space visible. It may take a bit of jockeying of some of your devices, but if you can't, that's fine. You just do the best you can. You try to get an angle that works to show your face and as much as your upper torso and your arms as possible. Sort of like me, I've got my face and my hands, and if I move back just enough, you could probably see my writing space, but I'd have to, of course, move this over so you could see it. But I know some people are on devices such as laptops, in which case you got to angle the screen just right. But if you're angling the screen, you won't be able to read the questions if you're trying to show your writing space. So you do the best you can. You do what the best you can with the equipment you have, and which still allows you to read the questions and do your best on the exam.
Thank you.
Oh, you're welcome. If for any reason during the Zoom session you lose internet connection or you start having bandwidth issues, your absolute and utmost priority should be the exam itself. Being on the Zoom session, that is secondary. So if you've lost internet connection, just focus on getting that exam back, getting that upload screen back, being able to upload your solutions to the questions. Don't waste time trying to figure out how to get back into the Zoom session. Technical difficulties will happen for some of us, and I just want you to know upfront that your priority should be just to focus on getting your exam complete. The being on the camera and whatnot, in the moment where you're just trying to get things done, you put that on the side burner. That's not your absolute priority. I know I've had in the past where students started to panic that they couldn't get back into the Zoom session, and they were spending more time doing that than they were trying to write the exam. So just take a deep breath and just say, what's my priority? My priority is to get my exam written and scanned and uploaded. Whatever else needs to get done, that will get put on the side burner, because right now I'm working in emergency mode. So hopefully that makes sense. If you have issues with uploading at the end of the exam, you just keep trying. So the idea is so the exam will be split up by question number in terms of the upload fields. And once you upload a question to an upload field, then as soon as the deadline has passed, that upload field gets locked and it just takes your last submission. So let's say, for example, you're running into technical issues and you haven't been able to get everything uploaded, and you're down to the final seconds, and all of a sudden things time out and you haven't even uploaded question 5. That's all right. You can still upload it after the deadline has passed, as long as you haven't uploaded something to that field before the deadline. So fields remain open past the deadline as long as nothing's been attempted to be uploaded to them before the deadline. If you've uploaded something before the deadline, then it just locks down right at the deadline. So what that means is you can still upload past the deadline. There will be an automatic penalty applied. I think the penalty was 10% per minute or something to that effect. Once you've got things uploaded, then just send me a message. Send me a Canvas message that says, I had some issues uploading. My apologies, I'm 1 minute late. And I will take care of reversing those penalties. So I guess what I'm trying to say is, don't go into a big panic. Just take a deep breath, try to get things finished, completed, and uploaded. And then after the fact, you can send me a message detailing the technical difficulties and things like that. So the idea is Canvas message. No, it just means in the inbox tool. So I will just bring that across here. So in Canvas, there's this inbox tool. You can see it down here on my left-hand side. I've got 3 messages waiting. So that's where you would send me a message. It's basically email within Canvas. All right. Okay, so the idea is to try, I want to reduce the amount of stress involved in all of these other things that aren't usually present in a face-to-face environment. In the face-to-face environment, you come into the classroom and the environment is essentially what it is. You don't have to worry about all these extra peripheral kind of things. But in this online environment, stuff can happen. And so I just want you to realize that focus on the exam itself, and everything else we can talk about after the fact. All right, let's get into today's topic. So as I said, so I was having some discussion with some colleagues, and we were talking about eye strain and eye fatigue, and having multiple Zoom sessions of classes a day. For many of you, that white background can sometimes be very difficult on the eyes. So I'm going to try a dark theme today. I've just converted my slides so that dark background and a little bit lighter text on that. And if the majority of you like it, then we can run with it. If many of you come back saying you like the white better, then we can certainly revert back to the white. I'm fine either way, personally, but I know some of you are on multiple Zoom sessions per day, and this is your early morning one probably. So we'll just let me know in the comments, and even after the fact, you can send me a message letting me know if you have a preference one way or the other. Okay, so what we're going to do today is we're going to get into the topic of tangent planes. I'm just sorry, I'm reading the comments here. Yeah, no, I agree. Yeah, it's about the light. So the whiteboard, looking at a whiteboard in a classroom, it's about the reflection of the light off of the board. So your fluorescent lights in the room and the reflection off the board. Whereas here, you're just getting that light beamed right to your eyes. So yeah, I don't know. It has something to do with the screen and probably the amount of blue light that comes out of it and contrasting lights, etc. Okay, so we're going to look at tangent planes to a surface. And as I said, we've already covered pretty much all of this in the last lecture with that single picture. But I'll do the single picture again because I have it all queued up and running. So let's bring it over here. So the idea is we have a point on our surface, and what we're going to do is we are going to take a plane. In this case, I'll take the other plane. Where are you, other plane? It's probably sitting above here. There it is. So this is a plane that passes through that point and is parallel to the XZ plane. And the intersection of that plane with our surface produces a curve. So we can draw our curve. There, I've drawn it in black. Now we've got a space curve. With a space curve, we can find a tangent vector. So we can find that tangent vector there. And that gives us a vector that points in the direction of the surface along the direction parallel to the XZ plane. So what do I mean by that? I've sort of said two directions in some sense. What I'm saying is that if I look in the direction parallel to the XZ plane, so along a constant y value, this tangent vector in some sense points in the direction of the slope of that curve. And so this is actually giving me a tangent vector to the surface at that point. But I can also find another tangent vector to that surface by looking at another plane and another space curve and another tangent vector to that space curve. And so we get these two tangent vectors to the surface. And once I have two vectors, which are both tangent to the surface, those two vectors form a plane, and that'll be the tangent plane to the surface. So that's this one here. That tangent plane, in order to describe it, we just need to know a point on it, which we have. That's the point we're constructing all of these things at. And we also need to know a normal vector. But the normal vector is just going to be the cross product of those two tangent vectors. So we can find our normal vector by taking a cross product. And I put it in purple to indicate that this purple vector is the information that contains the direction that this plane is going in. It's the normal direction of that plane. So this tells us that we can take our space curves, do the calculus that we've done with space curves, finding tangent vectors, and construct tangent planes to surfaces. Now the question is, this green and this red vector are the two tangent vectors. What direction do they point in? And how does that relate back to the original surface? And the original surface is given by a function f. So how do all those things relate to each other? That's what we can now work out. So let's get a picture drawn for this. So we got our surface. And we'll put some coordinate axes in here. So that's our x, y, z axes. We've got a point on our surface. And what we did was we constructed a couple of lines. The lines that are not lines, sorry, the curves that we constructed was a curve that looks like this. This was the one that we obtained by taking the plane that is parallel to the xz plane and passing through that point. So let's just label this point something. I'll call this point x naught, y naught, z naught. That's that point. So then this curve would be given by z is equal to fx and then y naught. So I'm taking the y value to be constant. That's how I construct that curve. And I can do the same thing in the other direction as well. So we get a curve that looks like this. This is z is equal to fx naught y. Now that curve I can write down a parameterization of. So we'll do the first one. The parameterization is going to be r of t, so we'll use t as our parameter. And what is it? Well, I'm going to let t, the parameter, just be the variable that allows me to change the x-coordinate. So I'm just moving, I'm imagining this curve, if it's parallel to the xz plane, then the x-coordinate can be my parameter. And the y value for all points along that curve are just going to be y naught. But the z value is going to be given by f, the value of our parameter, and y naught. So that's a parameterization of that first curve. And so from that parameterization, we can get the tangent vector. What's our tangent vector? It's just going to be given by r prime of t, which is given by 1, 0. And now I want to take the derivative of that function. I'm thinking of y naught as a constant. T is the variable I'm differentiating with respect to. But if I think back to partial derivatives, that's exactly what a partial derivative is. This is the partial derivative with respect to the x variable with t y naught plugged into that. So that's my tangent vector, and then I can work out the tangent vector, that's supposed to be an at symbol, at x naught, y naught, z naught, the point I'm interested in, what our tangent vector is going to be. Well, that value of our parameter t is now going to be x naught because it was the parameter which encoded the x value as I moved along the curve. So this is going to be 1, 0, the x partial, x naught, y naught. So that's my tangent vector at the point that I'm interested in. So that's this thing here. I'm going to call this, let's call it T1 for our tangent vector in the first direction. So we'll call it T sub 1. Then we could do the same thing in the other direction. So we'll go, for this one here, we could do a parameterization. Our parameterization in this case, maybe I'll put an r sub 2. If I go back, maybe now that I'm thinking I want to use r again, okay, maybe I'll go back and I'll put r sub 1s on each of these functions up above for my parameterization of the first curve. And then here's my second curve, r sub 2. And that one's going to be in the direction parallel to the yz plane. So that's where the x value is constant. So it's x naught. T is now the parameter which represents the y value. And then I get f x naught t. And then I can get my tangent vector, or my derivative. In this case, that's the derivative with respect to t. So that would be 0, 1, the y derivative, x naught t. And now if we're interested at the point x naught, y naught, z naught, then that's r2 prime of y naught, which is equal to 1, 0, f sub y, x naught, y naught. And that's our other tangent vector. Let's call this guy T2. And so that's this tangent vector here, T2. Now that I have those two tangent vectors, what I need to do is I need to find the normal vector to the surface. So I'm looking for this vector now. And that's going to be perpendicular to both of these tangent vectors. So that's my normal vector, which I can obtain by taking the cross product. So my normal vector is going to be the cross product of T1 and T2. So that's going to be I, J, K, 1, 0, F sub x, x naught. I'll move this over a bit. I'm drawing it a bit too close. X naught, Y naught. And 0, 1, Fy, x naught, Y naught. And that cross product now we can work out. What do I get? So cover up the first column, take the determinant of the 2 by 2 submatrix on the other side. That gives me a negative F sub x, x naught, Y naught. And if I keep going, I get a negative y, x naught, Y naught. And then I get a 1. And so there's my normal vector. So from this picture, and using our space curves and just taking parameter slices in directions that are parallel to the x and y axes, I'm just taking directional slices along the surface through the point in certain directions and using space curves to find the slopes of those curves, and then using those two directions to get me a normal direction for what the tangent plane should be.
Dr. Mohola?
Yes.
Hi, this is Nilufar.
Hi.
So for T2, last line for T2 shouldn't be 0, 1.
Ah, yes, it should be.
Okay.
Thank you.
No problem.
Yeah, there's a mistake here. Thanks. Oops, my eraser's a little bit big. Let me shrink it down. Yeah, copying error. For some reason, I switched these two. So I'll put it in a different color here. So that should be a 0 and a 1. Yeah, thanks for pointing that out. Okay, so now we've got a normal direction and we've got a point. That's the x naught, y naught, z naught. And this tells us, up at the top, this tells us how we can therefore write down the equation of the tangent plane. We need the normal vector. We do have that. That's capital A, B, C. That's given by the partial derivatives at the very bottom of the page. And we need x naught, y naught, z naught, which we have. That's a point on the plane. So we can put those things together, and I'll write it down here. And the reason I'm writing down here is because I've basically written it in that box there. That's the final result. And so we're pretty much there with the final result. I'll just say, what is our tangent plane? That is negative the first component of our normal vector. Sorry, I shouldn't say negative the first component. Negative is the first component. So negative the partial of f with respect to x times x minus x naught, and then plus negative f sub y, x naught, y naught, y minus y naught, and then plus the third component of our normal, which is 1 times z minus z naught, and that's equal to 0. So that's just using the equation of the plane. And now we can rearrange these things. We've got some negative signs here. So I could take those first two terms, move them to the other side of the equation. And so if I push those to the other side of the equation, I get only left on this side is z minus z naught, and the other side I get f sub x, x naught, y naught. times x minus x naught plus f sub y, x naught, y naught, y minus y naught. And that's the equation of our tangent plane. And so that's what we've summarized here in the box. The tangent plane for a surface given by z equals f of x, y at a particular point is given by z minus z naught is equal to the x derivative times x minus x naught plus the y derivative times y minus y naught. Notice the similarity to Calc 1. The tangent line at x naught, y naught to y equals f of x is y minus y naught is equal to the derivative at x naught times x minus x naught. And so all that's happened here is we've just added another term on. Instead of y minus y naught equal to the derivative times x minus x naught, here we've got our variable, output variable is z, and it is equal to, or z minus z naught is equal to the combination, the linear combination of these two partial derivatives. So it's just a very natural step up into the next dimension. And now we can probably see how to extend this to further dimensions, tangent spaces and higher dimensions. We just keep adding the terms involving the derivatives of the other variables. So there's our tangent plane. Let's go ahead and do an example where we compute one. So find the equation of the tangent plane to this surface. So here we've got our function f of x, y is the square root of 4 minus x squared minus 2y squared. So there's our function. We want to find the tangent plane to that. We need to know its partial derivatives at the point, and we then just need to piece them all together. So we'll first compute the partial derivative with respect to x. So that's going to be the derivative of the square root function, which becomes that thing raised to the negative 1/2, so the square root moves downstairs. And then I get the half coming out front because that was the power when I used the power rule to drop the half down. So that's the derivative of the outside function times the derivative of the inside function. And that's going to be negative 2x. So this becomes negative x over the square root of 4 minus x squared minus 2y squared. And now we're interested at the point 1, negative 1. So f sub x, or the x derivative of 1, negative 1. We're going to plug in 1 and negative 1 for our values. So that's negative 1 square root of 4 minus, and that's 1. I won't even bother putting the brackets in there because it's an x squared, so that's going to be a 1. And then a minus 2y squared is a minus 2. So this becomes a negative 1 as our final
Professor?
value. Yes?
Why is square root of 4 minus x squared minus 2y squared in the denominator?
Why is it in the denominator? Because I'm thinking,
Yeah.
so we just took a derivative. So I'm using this fact here, that the derivative of the square root of x is 1 over 2 root x. And
Okay.
so that's the power rule. If we want to think of it as writing it as x to the 1/2, then the derivative of that is the half comes down, and then we take 1 away from the exponent. So the new exponent is x to the negative 1/2. And so that means a 1 over a square root.
Okay. Thank you.
You're welcome. How about our y derivative? So that's going to be almost the same. It's 1/2 square root 4 minus x squared minus 2y squared, except now we're taking the derivative with respect to y. So the derivative of the inside function becomes a negative 4y. So that becomes a negative 2y square root of 4 minus x squared minus 2y squared. Or in the particular case where we're looking at 1, negative 1, we get the value of 2 over square root of 4 minus 1 minus 2, or in other words, 2 as our value. So there's our two values of our partial derivatives. So we can now do the tangent plane. And it's z minus the z coordinate of the point is equal to the x partial times x minus the x coordinate of the point plus the y partial times y minus the y coordinate of the point. Or in other words, z minus 1 is equal to negative x plus 1 plus 2y plus 2, or x minus 2y plus z is equal to 4. And so there's the equation of our plane. And let's
Do
see.
we want to write it in general form every time, or is it
it's fine.
the tangent plane?
Yeah, it's fine to leave it in the first form above. That's perfectly fine. I'm just looking, do I have a mistake somewhere? Because I'm getting that my point, let's see. Nope, everything looks fine. So I'm just doing a quick mental check at the end just to make sure my point lives on this thing. So plug 1, negative 1, 1 into it. And I just did a miscalculation in my head. But if we plug 1, negative 1, 1 into it, we get 1. So maybe I should just say what we're doing here. Check x equals 1, y equals negative 1, z equals 1 satisfies this just by plugging it in as a quick mental check at the end, just to make sure that you haven't made any small errors. But yeah, your question, certainly we could leave it like this. And in fact, on an exam, for example, if you're ever asked to write down the equation of a plane for something, hint, hint, you're probably going to, no surprise, you're probably going to be asked to find the equation of a plane. Not a tangent plane, of course, because this material is not covered, but just a plane itself from the chapter 12 material. You can certainly leave it in that first line form where it's just unexpanded out. You don't have to bother multiplying out the normal vector to the components of the normal vector across the x minus the x naught values and y minus the y naught values, etc. You can certainly leave it in that form because that shows what the equation of the plane is, and it actually tells us more. It tells us how you found it, how you structured your plane as a combination of the normal vector and a point on it. Unless we're going to do something with the plane, then there's really no reason to simplify it. If I wanted to plot it, for example, then I would simplify it because it's easier to type that into a plotting program. All right, let's have a look at the next term. And this is linearization, much like we had in Calculus 1. We can take the tangent plane. So I'm going to scroll back here for a second. We found a tangent plane. And what we can do with this tangent plane is if I solve for the z value by just moving z naught across to the other side. And if we think about what z naught is, that's f of x naught, y naught. That's just the function value at the input x naught, y naught. So if I move that to the other side, then that gives us just another rewritten form of the equation of the tangent plane. But that tells us how z on the plane is a function of x and y. So that tells us an equation for the plane as a surface. And that's the equation we're just writing down here. We're saying, well, why don't we take that new function, which is our, this is just our z naught term from above, and move it to the other side. And so now we get this function in x and y, which is a linear function. It describes a plane, and that's what we call the linearization of f. It is the tangent plane for the function at a particular point, but it is a function in and of itself, so we call it a linearization. And we can use this then to do things like linear approximation. So what is linear approximation? Well, it says take your curvy object, your surface, and approximate it with a flat thing, a plane. And so there's the approximation symbol, these sort of squiggly equal signs. And so all we're saying here is that the function itself, f of xy, is approximately equal to the linearization. And the linearization, we've got a description for it as a function, as a linear function, because it was what we got from the tangent plane representation. So this is called the linear approximation to a function. And this is, if you want to think about sort of in general terms, this is what calculus is all about. It's taking curvy things and trying to approximate them with flat things. And so this is taking a surface and at a particular point trying to approximate it by a flat thing. This is how, you know, programs like, if any of you are familiar with ray tracing programs, so this is the idea of you build or construct a three-dimensional scene using software, and then you try to render that scene as a two-dimensional image by positioning a light and shining rays of light on the objects in your scene and looking how they reflect and bounce back. And that sort of tells you how shadowing effects occur and all of that. So this is how these three-dimensional software rendering packages work. These are called ray tracing programs. And this is at the heart of them, because what you have to do is you have to figure out, for a given surface, a light ray is coming in. How does it bounce off that surface? Which way does it go? And the way you do that is you take a little tangent plane at the point of impact where that light is hitting the object. That tangent plane is now a flat object, and the ray of light is going to bounce as it would off of a flat object at that particular point. And so that tells you how the light would get reflected, because now you just have to work out angles between a line and a plane. You don't have to worry about angles between a line and a surface anymore. So you work out an angle between a line and a plane. And so that's where these linear approximations really come in, is to take curvy things and approximate them by flat things, and then use the flat objects, which are more easy to work with. Okay, so let's have a look at doing a linear approximation. So let's find the linear approximation to this particular function at the point 1, 2. So here I've got my function f of xy is equal to 2x cubed plus 2y cubed minus 9xy. To find the linearization, I need to know the x and y partials. So that's 6x minus 9y. And so in particular at the point 1, 2, that is 6 minus 18, or negative 12. And then I need to know my y partial. That is 6y minus 9x, or f sub y of 1, 2 is 12 minus 9, which is, let me make sure I got this right, 12 minus 9, looks like that should be 3. Did I get this right? Oh, sorry. I'm terrible. For some reason, I started reading these things as squares a second ago. Let me just fix this. Got a few mistakes here. The derivative of the cube is a square. And same with the derivative of the cube here. That's a square. So I missed those things. I got to fix these values. And the first one, it didn't matter because it was just a 1 that was being squared. So the first one's fine. The second one, there's an error here. My mind was telling me one thing. So it is 6 times 2 squared minus 9. Okay, so that's 6 times 4 is 24, minus 9 is 15. So there's our new value, 15. Okay, looks like we've got everything fixed. Now we're still looking for the linear approximation. So that's L xy. that's given by the function value at 1, 2, plus the change that occurs when you move away from that point. If I move a little bit in the x direction, how much has my z value changed? It changed by the x derivative. If I move a little bit in the y direction, how much is my function value z, or the z value changed? It changes by the derivative of the y value. So this is f sub x times x minus 1. So that tells me if I take my x value and I move it a little bit away from 1, then the amount of jump I take in the vertical direction is the x derivative times the change in the x value. How much do I move in the vertical direction when I change my y value? I change by the derivative times how much I've moved in the y direction. So those are just sort of a way to think about these things visually. What's f of 1, 2? So I'll go back up to my function. That's 2 times 1 cubed plus 2 times 2 cubed. So that's 2 plus 16, or 18. And then 18 minus 18 is 0. So that's a 0 value there. Plus the x derivative, which is negative 12 times x minus 1, plus the y derivative, which is 15 times y minus 2. And so there's our linearization. X minus 1 plus 15, y minus 2. So that is the tangent plane at the particular point 1, 2. And so the values on this tangent plane, or this linearization, should be close to the values on my surface. If the tangent plane is really a tangent plane, that means it does a good job of approximating the surface near the point 1, 2. So the values coming out of this linearization should be close to the values on the surface. Now this is asking us to approximate the y-coordinate of the point that belongs to this particular curve, 2x cubed plus 2y cubed plus, or minus 9xy equals 0. So that means what we're interested in is we're interested in the case when z is equal to 0, because that curve that we're looking at in the last sentence of the question has the z value 0. This value right here is the z value. So when z is 0 and x is 1.1, we want to know what the y value is. So what we'll do is when z is 0 and x is 1.1, the y value is approximately, well, it's approximately given by the value we would get on the linearization. And so that means the output would be 0. We would have a 1.1 minus 1, and then a 15 times y minus 2. So it's approximately, the y value is approximately the value of the y that satisfies this equation. And then we can solve for y, and we get that y is equal to 52 over 25. So this is the approximate y value. So again, the idea here was we had a surface and we had a point on the surface. So we construct a tangent plane at that point. That's called the linearization. And our surface is approximately, all the values on our surface are approximately the values they are on this plane. And so we can use the plane as a proxy for the surface, as a close approximation. Can we visualize what that would look like? Absolutely. So what we can do is we could plot these things, for example. I'm just going to bring this across. So our surface is 2x cubed, so 2x cubed, and then plus 2y cubed, and then a minus 9xy. Okay, so that's our surface we're dealing with. We are interested in a particular point. The point we want to worry about is going to be 1, 2, and we found the value to be 0. So if I look at, there it is right there. So I will extend the y value out and the y and the x value out a little bit just so it's on that point. So it captures that point. So there's our point there. And then we constructed a tangent plane. So I will construct the explicit surface because we've written it as a explicit surface. We've written it as L of xy, or the z value, is equal to -12 times x minus 1, and then plus 15 times y minus 2. And again, I'm going to have to jump these up just a little bit because we're sort of at the edge of where we want to be. So we can see at that point now, we've got this tangent plane. And the idea here is that this tangent plane is so close to the surface at this point that all the values, really the only point that's in common between the two is the point we took the point of tangency at, so 1, 2, 0. But all the other values on the surface are really close to the values on the plane in a small area around it. So if I move out 1.1 in the x direction, so this is the x direction here. If I move out 1.1 along the x direction, so just a little bit along the x direction, then what is the value that I'm interested in? I'm still keeping my z value at 0. I want to know what the corresponding y value is. So if I move out a little bit here, I'm going to plot another point. This is going to be 1.1. 0 is still z, and the y value is 52 over 25. Let's see. Sorry, I got those backwards. Thanks. That's the y value, and that's the z value. So this value, which we found on the plane, is really close to the value on the surface. I didn't know what the y value was on the surface because that would involve solving the original equation for y, which was a harder problem. So instead I used the values on this plane, which is a linear object, easier to solve for different values. And so because these values are so close to each other, I'm using one as an approximation of the other. So that's the visualization that we're having. All right, let's have a look at the next idea. So this idea of increment, these are all analogous to things in Calculus 1. So what the increment delta z is just the change in the z value. If I've changed my input value starting at a and I move over a little bit to x plus delta, or a plus delta x, and I also change my y value from an initial value of b, nudge it a little bit over to a b plus delta y, then how does my height change? So again, we can draw a picture that sort of represents this idea. We've got our b value, our a value. So that's AB in the plane here. And now I'm imagining that from that input, I go up and I get my corresponding function value. That's going to be our f of AB. And then what I can do is I can move over a little bit. What happens if I nudge over to an a plus delta x and a b plus delta y? And look at this new point, a plus delta x, b plus delta y. And I go ahead and I construct the function value at that point. Maybe I'll put it up here, f of a plus delta x, b plus delta y. The question is, how much did the z value change? what is the change that happened here between this value and that value? How much height got added or subtracted off? That's delta z. That's what delta z is. And so that's just obtained by taking the difference of these two values. So that's what we call the increment of z. If we change the inputs just a little bit, how much does the output change? And it changes by delta z. Okay. Now, we will come to this notion of what it means to be differentiable, and that has to do with this delta z. The idea with differentiability is, unlike in Calculus 1, where we say a function is differentiable if its derivative exists, that's not the case here, because the only derivatives we had so far are just an x derivative and a y derivative. And both of those can exist without the function actually being differentiable. So we have to redefine what we mean by being differentiable. And that's this definition here that says z is differentiable if the increment delta z can be expressed in this form. Derivative of x times delta x plus derivative of y times delta y plus some small values which go to 0 times delta x delta y. I will just summarize this by saying, what does this mean? This means the surface is approximated by a plane, I should say. No, I won't say tangent plane, I'll just say plane in general. And then I'll end with one picture. And so here's a picture. I'll write this one down next Wednesday. But the idea is, if I look at this function and I look at the point 0, 0, it looks like I won't be able to approximate it there with a plane because there's so much sort of crinkling going on at that point. Looks like we've taken a piece of paper and we've put some harsh crinkles in it. So if I zoom in far enough, this is not going to become flat. This is still going to have these sort of crinkles happening here. And so that's an example of a function that's not differentiable there, because if I zoom in and zoom in and zoom in, it doesn't become flat. It doesn't look like a plane. It's kind of like the absolute value function. If I zoom in and zoom in and zoom in, I never get rid of that point, that vertex where these things are sort of bending at. The same idea is happening here. We define differentiability to be that if you zoom in far enough and it eventually looks flat, then it's differentiable. If you zoom in and it doesn't look flat, it's not differentiable. And this is different than the x and y partials existing, because here, each derivative is 0 along the axes, because it's just a straight line. If we plot these things, we'll see that their curves are just straight lines. So the derivative, x derivative and y derivative, are both 0 at that point. But yet, it's not differentiable because of the crinkling nature. It's because of all these different directions that are really happening here. It is continuous. Yep, this is continuous because the limiting value at 0, 0 is 0. The function value is approaching 0. So this is continuous. The x partials exist. The y partial exists. And yet it's not differentiable because it crinkles in some way. It's not going to eventually become a tangent plane. And that's the subtle definition of differentiability that we have to accept in this course as opposed to Calculus 1, is that we've got a lot of different directions we can approach at. And so there's some subtlety here. So our definition is it's differentiable if you zoom in far enough and it eventually looks flat. All right, so we'll call it today. I'm just going to stop the recording.